Hi everyone, welcome to lecture 7 of Math 1B03. Today's lecture will be on linear independence, and this material is based upon section 1.7. You'll notice that we're skipping section 1.6 for now, but we will return to it in a couple lectures. Now today's lecture, the main topic or definition that we want to learn about is linear independence. And as I have written right here, that this is a key concept in linear algebra. So today we're going to see what linear independence is. We're going to look at some examples. We'll look at what happens for small sets of vectors and when those sets are linearly independent. We'll look at some of the geometry, and then we'll look at some conditions that force sets of vectors not to have linearly independence. So jumping in, let's start with the definition, which I've already written out here on my sheet. So we have a set of vectors in Rn. So imagine some sort of Rn, and you're imagining a collection of vectors in that Rn. And we say that those sets of vectors are linearly independent if when you look at the vector equation, x1 times v1 plus x2 times v2 up to xn vp equals 0. So we're asking what values of x can I fill in to make this equation true? The only solution that works is the trivial solution. Because clearly when we plug in all zeros, we get 0, but this is the only solution. And if star has a non-trivial solution, if somehow we can find xi's that we can plug in and make the statement true, where one of the xi's is not 0, then we say that the set of vectors v1 through vp is linearly dependent. So let me give you an example. Something that's linearly independent and something that is linearly dependent. So here we have two vectors, 1, 0 and 0, 20, 20. And what we want to do is show that these two vectors are linearly independent. So we want to look at solutions to x1 times the first vector plus x2 to the second vector. And we want to know is, when will x1 and x2, what values of x1 and x2 will allow this to equal to 0? But before we set it equal to 0, let's just actually expand out what this is. We'll end up with x1 in the first coordinate, and in the second coordinate, we will have 20, 20 times x2. And we want this equal to 0, the 0 vector. So if we look at this component-wise, what we need is x1 to be 0. This will only work if x1 is equal to 0. And if we look at the second equation, we get 20, 20 times x2 is equal to 0. So we have that x2 is also equal to 0. So we get only the trivial solution. So these are the only values of x1 and x2 that I can put in to make this equation true. So these two vectors are linearly independent according to the definition because the only solution to the vector equation is the trivial solution. Let's look at the second batch of vectors. So here we have three vectors, 1, 0, 1, 2, and 6, 10. And what I want to do is show that it is linearly dependent. So what we want to do is actually translate this into something that we already know how to do, which is a system of linear equations. So note, what we're trying to do is try to solve this equation. x1 times the vector 1, 0 plus x2 times the vector 1, 2 plus x3 times the vector 6, 10. We want to be able to see if we can find x1 and x2, x3 so that we can get 0. We can find some sort of linear combination to make this true. Now we step back and we notice, well, this is really a matrix equation, right? We could rewrite this as a matrix equation where my matrix, it has first row 1, 1, 6 and second row 0, 2, 10. And I'm multiplying it by the vector x1, x2, x3, and I want to set that equal to 0, 0. Of course, we could just now use Gaussian elimination, learning from the material from the first two lectures, right? Because we have a system whose augmented matrix now looks like this. So this is my augmented matrix. So we'll put some dots there to keep track that it's augmented. We row reduce this matrix. So I can do 1, 1, 6, 0, and 0, 1, 5, 0. And already we see that because I have a pivot here and I have a pivot here, I actually have a free variable. X3 is free, right? And what we know is that if you have a free variable, then you actually have an infinite number of solutions. Okay, so an infinite number of solutions. So what that means is that not only can you find a non-trivial solution to this system, to this vector equation, you can find an infinite number of equations. Now let's actually go a little bit further and just kind of mine out what we can get from here. So I'm going to put this into row reduced echelon form. So here we go. This is into row reduced echelon form. We already said that x3 is free, so that means that x1 is equal to negative x3. We can see that from this augmented matrix. And x2 is equal to 5 minus x3. And I'll go over to my next page to finish up here. We have so all solutions have the form x1, x2, x3 equaling to x3 times the vector negative 1, 5, and 1. So if we're looking for any specific non-trivial solution, we can pick any value of x3 that we want. So a specific non-trivial solution when x3 is 1 gives minus 1, 5, and 1. So going back, just to go back to the question here, is we had to show that these vectors here are linearly dependent. So we needed to find a non-trivial solution to this equation. And we know that there's actually going to be an infinite number of solutions because it has a free variable in our system. And I gave you a specific solution right here. So these vectors are definitely linearly dependent. So we're going to take a little break here before our next video, but what we want to do, what we're going to kind of summarize is notice that questions about linearly independent somehow can be rewritten into into a matrix vector equation. Okay, I will see you in the second part of today's lecture.